So good afternoon, everyone. Welcome back to Math 122. Today's our last day of actual class because Thursday this week is going to consist of a review, I think. Am I right about that? I'm pretty sure I'm right about that. So next week is dead week, right? So there's no class on next Tuesday, right?
Yeah.
Because that's like a reading day or something. So yeah, today's the last day that we're going to learn new things. I've returned to you all the exams, which I was fairly happy with. The average was lower than the first exam, but that was 100% expected. I still think that our average was pretty great overall, so I'm happy with it. So great job to all of you. What else? So let's talk about what the end of the semester is going to look like. So today we're going to learn the last little bit of things. I guess I don't have a title card for today. Let me go back to this one. And we'll modify it slightly. So today we're going to learn basically 6.3, and that's going to be the end of the class. Your final exam is May 2nd at 4 p.m. in this classroom, 2.5 hours. The length will be like 1.5 times the length of a regular exam. So basically double the time. Sorry? It's May 2nd. Yeah, I just checked it earlier today. It's May 2nd at 4 p.m. So office hours are going to be the same until that day, and including that day, because I think that's a Tuesday, right? Come on, now I got to look. Why am I looking at August? May 2nd is a Tuesday, so yeah, I'll be in the Math Tutoring Center that morning as well. So office hours are going to remain the same. Math Tutoring Center, their hours are going to remain the same. SI, there's not going to be a special dedicated final exam session for the SI, but for other SIs there might be, so Jacob, just whenever you get that information, you can share it with the class. I posted a homework, okay? Whoops. So the final homework is due, I think, April 26th at 11:59 p.m. So, I mean, realistically, you could do it tonight, but I just figured why not give you more time to do it. So, as far as I can tell, there's no provisions in the university like regulations that say that there shouldn't be an assignment due at this time and day. So if there are that you're aware of, please send them to me, because I looked everywhere and I couldn't find anything, so I think it's okay. I mean, certainly there could be an assignment due this week, but I wanted to give you more time to work on the problems. So that's the last homework. So the final exam will have probably a couple questions or a few questions from this final homework assignment to measure your retention of the information from exam 2 up until now. So that's the last homework. All of your opportunities to study with me are going to be these office hours this week and next week. And on Thursday this week, we'll have a review session as well. So when you come on Thursday, please do bring some questions about some things that you want to talk about. So that could be something as simple as, I don't really have a good grasp of the fundamental theorem of calculus. Can you talk about that? Or you can say, I have problem 3 from this homework that I didn't understand. Can you please do it? So anything like that, you can bring to class on Thursday, and I'll try to help with. So And that's going to pretty much be the end of the class. So it's been a good ride. Are there any questions or comments or concerns before we move on with content for the last day of class? All right, it doesn't seem like there are, so let's talk about more integration stuff. So before we talk about that, I'll quickly review what we talked about last time. So I kind of sped through a couple of things at the start, namely the units of integrals and interpretation of integrals. Okay, we also learned about the fundamental theorem of calculus, okay, and total change. And we also learned about the average value of a function over an interval. And after that, we switched gears to chapter 6, which is about, well, we talk a lot about these integrals, but so far we don't know how to do them. So we finally learned how to do them, okay? Well, and we started with the idea of antiderivatives. So antiderivatives are like the opposite of derivatives, right? So we want to find a function whose derivative is our original function, right? So for example, x squared is an antiderivative of 2x because 2x is a normal derivative of x squared, right? But one of the things that we learned is that we have to use this language like an antiderivative and not the antiderivative, because there could be many, many different antiderivatives for a function depending on whether our antiderivative has a constant in it, right? Because constants, when we take the derivative, they'll just go right away. So it's hard to tell, well, is this the derivative of x squared plus 3, or is it the derivative of x squared plus 5? We don't really have a mechanism of identifying the unique antiderivative, unless we have further information, which we'll learn about today. So that was antiderivatives. We also talked about the difference between definite and indefinite integrals, okay? So for definite integrals, we refer to a number, okay? So definite integrals have bounds of integration, namely a and b here, and the result of this integration will be a number which represents the area under this curve. Or if your function is sometimes negative, then it's the area above the x-axis minus the area below the x-axis. And then if we don't have bounds of integration, then we call the integral indefinite, okay? And an indefinite integral, so this is all just notation. So this is the way that we write, basically what we're referring to here is a class of functions. It's the class of all functions, capital F of x, whose derivatives are little f of x, okay? So for example, the indefinite integral of 2x dx is the family of functions x squared plus c, where c is any number. Okay, so that was definite and indefinite integrals. So in order to do some, well, first of all, we learned some properties of integrals, which is namely that the integral of a sum is the same as the sum of the integrals, and vice versa. And also the integral of a number times a function is just a number times the integral of that function. So these are the same kind of rules that we saw for derivative functions. We also learned that the integral from b to a of f of x, if we switch the upper and lower bounds, then we actually get the negative of the original integral where the bounds go from a to b. And finally, we learned three derivative rules. Sorry, antiderivative rules. So we have to reverse the the derivative rules. So for the power rule, when we do derivatives, what do? We take the power down and we make the power 1 less. For antiderivatives, we're going to do the opposite of that. We're going to make the power 1 more and divide by the new power. And of course, we have to add c anytime we're doing an indefinite integral. And the e to the kx rule also got switched. Instead of just rewriting e to the kx and multiplying by k, we rewrite e to the kx and we divide by k. And of course, we have to add c. And then the integral of 1 over x dx, we want to find a function whose derivative is 1 over x. That function is the natural logarithm. But crucially, we always should use our absolute value signs here, unless we have some condition which tells us like x is larger than or equal to 0, then you can go ahead and use the parentheses because it's sort of redundant. But otherwise, we need to have those absolute value signs on the input x. Okay, so that was what we learned last time. So we did a couple examples trying to do some integration here. So let me just do 2 examples really quickly of the ones we didn't do last time. So this first one, we want to do the integral of 2x times 3x plus 7 dx. And we're sort of stumped because we didn't learn any like antiderivative product rule, and we have a product of functions here. But that's okay because we can go ahead and multiply this product out and simplify the integrand. Okay, if we did that, we'd have the integral of 6x squared plus 14x dx. And then we just need to do the antiderivative. So 6x squared, we raise the power by 1. That becomes 6x cubed, and we have to divide by the new power. And then the same thing with the other one. We make the power to be 2 instead of 1, and we divide by the new power, and then we have to add c. So at the end, we get 2x cubed plus 7x squared plus c. Okay, and you can always check that your antiderivative is correct by taking the derivative of it. If I take the derivative of 2x squared, I do get 2x cubed, I get 6x squared. If I take the derivative of 7x squared, I get 14x. So that's how I can check my work. Let's do one more example. So for the other one, again, we don't have an antiderivative quotient rule, so I have to simplify this. Well, you can simplify this by breaking it up as x over x plus 1 over x dx, and then we can simplify further. The first term becomes just 1 plus 1 over x dx. And we know via the linearity of integration that this is the same thing as doing the integral of 1 dx plus the integral of 1 over x dx. Right? So I just need to find an antiderivative for each of these two things separately. And if I do that, I get x plus c plus ln, absolute value of x, plus c. But this time, since I split it up into 2 different integrals, I got 2 different constants, right, that are being added. But the thing is, they're both just numbers. So if I add one number to another number, I can combine them into just one constant. So I'm going to do plus c, where this c is a new c, which is the combination of these two. Okay, so usually we just write c once. Yes? I would not do 2c because technically, these constants could be different numbers, right? It could be C1 and C2, and then this one would be like C3, which is some other constant, which is whatever you get when you add them together. So for example, I could take my antiderivative of 1 to be the function x plus 3. I could take my antiderivative of 1 over x to be the function ln absolute value of x plus 5, right? If I did that, then this one would be 3, this one would be 5, and this one would become 8. But the point is that they're all just a number. So whichever numbers I choose, it doesn't really matter. I'm going to be able to combine them into some other number, right? Does that answer your question? All right. Are there other questions on these first 2 examples here? All right. If not, then the last step, or the last thing we're going to learn for today and for the class is 6.3. Oh, sorry. There's one other thing I need to talk about here. Sorry, 2 more things to learn. Then we'll be done. The first one is initial value problems. So we can single out one unique antiderivative of a function f of x if we are given additional information. So what do I mean by that? The two pieces of information I have are that the integral of f of x, the integral of little f of x is equal to capital F of x plus c. That's information number one. Piece of information number two is that f of a is equal to b, where a and b are given. Okay? So, we know that all antiderivatives of little f of x have the form capital F of x plus c, where c is some number. But we also have the information which tells us what is one value of the function for one input of the function. This will help us to figure out what c is, okay, what c is in the following way. So I'll do a couple examples to illustrate this. So first of all, if we want to find the unique antiderivative, okay, here's what we do. We want to do the integral of 2x plus 3x squared minus 7 dx. That gives us x squared plus 3x cubed over 3 minus 7x plus c. And that is capital F of x plus c. But we also know that if you plug in 1 into this function, then you get 10 as the result. So what we can do is we can say, well, f of 1 is what we get when we do 1 squared plus 1 cubed, because 3 over 3 is 1, 1 cubed minus 7 plus c, and we get 10. So f of 1 is equal to 10 tells us when we plug 1 into this function, then the result should be 10. And now you can see how we're going to be able to figure out what c is. Okay, what is the particular value of c in this case? So we add 7 to both sides, take away 2 from both sides. So what do we got? We really just got to take 5 away. Sorry, add 5 to the other side, excuse me. So we do minus 2 plus 7 to cancel this, and to cancel this, minus 2 plus 7 gives us 8 plus 7 is 15. So in this case, we say capital F of x is equal to x squared plus x cubed minus 7x plus 15. So in this case, we get one function as our antiderivative. It is the antiderivative of this function subject to this additional constraint. Okay? It's kind of like you add additional information to single out the correct one. It's like if I asked you, give me the name of the person in this room who has brown hair. Well, the question is wrong because there are multiple people in this room who have brown hair, right? We could say Dan, or we could say Dan, or we could say Owen, or whatever, right? But if I added the constraint, give me the name of the person in this room whose name is Dan and worked at the Masters recently, then we could single out that I'm talking about Dan O'Terry in the front right? So you add an additional constraint in order to make your question more specific. If your question is not specific, you might have too many answers, right? But if you add additional specificity to your question, then you can ask the right kind of question such that you only have one answer. That's what we're doing with initial value problems. Are there any questions on this one? All right. Then that's initial value problems. So now we're going to learn the actual last thing that we're going to learn in this class, which is the fundamental theorem of calculus slightly rewritten. And it goes like this. If capital F of x is a function such that the derivative of that function is little f of x, then what is going to be true? The integral from a to b, so now we're doing a definite integral. The integral from a to b of f of x dx, little f of x dx, will be equal to capital F of x evaluated at b and a, which this notation, let me remind you, means you just do f of b minus f of a, where b is the number on top. Okay, so why is this so interesting? It's interesting because this represents the area under the curve. And the fundamental theorem tells us if you want to know what is the area under a curve, all you have to do is find an antiderivative of your integrand and plug in two numbers. And then we get the answer basically for free. Okay? So let's see some examples of this in action. Is it okay for me to scroll down, or you need more time? Need more time? We good? Okay, I'm going to scroll down. So use the fundamental theorem of calculus to calculate the following integrals. Okay, easy peasy. All I have to do is find an antiderivative of the integrand. So in this case, the integrand is 8x plus 1. So I need to find an antiderivative of that. So I raise the power by 1 to make it 8x squared, and I divide by the new power. And then I'm going to add, what's the antiderivative of 1 going to be? Yeah, just x, because I need a function whose derivative is 1. If a function's derivative is 1, then that means that its slope is 1. So 8x squared over 2 plus x, evaluated at 0 and 5. So that means first I plug in 5. So I get, so let's cancel these two, that becomes a 4. So I get 4 times 25 plus 5 for my first thing. And now I get minus, when I plug in 0, I just get 0 plus 0. So this part just goes away. And I end up with 105. I end up with 105. Okay, so that's the true area under that function, which is just a linear function, from 0 to 5. So one thing that I want to point out here is that we just need f of x to be a function whose derivative it's little f of x. We're not saying the antiderivative, we're saying an antiderivative in this case, because actually we can use any antiderivative that we like. And let me show you why. So another antiderivative of this function could be the function 4x squared plus x plus 71. That would also be an antiderivative of 8x plus 1. And if we were to do the same process, plug in 0 and 5, what would we get? We would get 4 times 25 plus 5 plus 71. And then we would subtract from that. When we plug in 0, we would get 0 plus 0 plus 71. What do you notice is happening here? Do we think we're going to get the same answer as we did before? I think so, because this minus sign is going to distribute onto the 71 here, and it will cancel with the 71 from the previous part, right? So we can use any antiderivative that we like. The easiest one to use is probably the antiderivative such that the constant term is 0. Okay? So we just choose c to be 0 when we're doing definite integrals. Any questions on this example? We feel okay about that? Because it's being added here, but it's also being subtracted. So this minus sign has to be distributed onto each of these three terms. So at the end we get 71 minus 71. So they cancel each other out. Any other questions? Okay, should we do one more example, or do we want to do group work? Who says one more example? Raise your hand up high. Who says go to group work? Hand up high. Okay, one more example, one out. So let's do one more example. We'll do part B. I'm going to delete this part. Okay, part B. Again, all I have to do is find an antiderivative of this function. So the very first thing I'm going to do is I'm going to use the constant multiple rule to pull that 5 out, because I don't like that 5. Now I just got 1 over t dt inside. And I know that 1 over t is the derivative of a function that I know. What is that function? Good. So here's some other notation that we sometimes use, is these brackets when we want to multiply something times 5. Okay, we're going to do ln of absolute value of t. And then another bracket, and I'm going to do 0, sorry, not 0, but 1 and e here. 1 and e. So now what that means is I need to do 5 times, and now I'm going to do, on the inside, I'm going to plug in e, and then I'm going to plug in 1 and subtract. So I plug in e first, so we get ln of the absolute value of e, but e is a positive number, so I don't really need the absolute value sign. I can just do ln of e. Minus ln of 1, also a positive number, so I don't need to use the absolute value sign. And now I just need to recall that ln of e is just 1. And what's ln of 1? Well, let's see how we would remember what to do if we didn't remember what ln of 1 is. Here's what we would do. We would say, well, I know that if ln of x is equal to y, then I raise both sides to the power of, as a power of e, and then I get e to the ln of x equals e to the y, and therefore x is equal to e to the y. So if I want to figure out what is ln of 1, then I say, well, if ln of 1 is equal to y, then e to the ln of 1 is equal to e to the y, and therefore 1 is equal to e to the y. So what power do I need to put here in order to make e to that number equal to 1? The power should be 0. The power should be 0 in order to make e to the 0 equal to 1. So this is 0. ln of 1 is 0. Okay, or if you want, you can remember the graph of the ln function, which looks like this. It goes through the point 1, 0, implying that if you plugged 1 into the function, you get 0 as the output. Okay, so at the end of the day, this is just 5. All right. Yeah.
So when you took 5 out at the beginning, do you know that you could do that on like the C equation?
Okay, so in this case, what I was thinking was I want to find an antiderivative of this integrand, but this 5 is really throwing me off. I know that I would be able to find the antiderivative of that thing if it was 1 over t, right? Because I know a function whose derivative is 1 over t. So we use the rule that we learned in the previous section, which is this rule, which says the integral of a constant times a function, you can bring that constant out of the integral, right? You can bring that constant out of the integral. Same kind of deal for when I do the derivative of something like, when I do the derivative of something like 52 e to the x, right? We can rewrite this as 52 times the derivative of e to the x, and then we just get 52 times e to the x, right? So same way that I can pull constants out of derivative operators, I can pull them out of integral operators. Any more questions on this example here? All right, if not, then I'm going to turn you all loose. I've taught you all that I can teach you. So I'm going to turn you loose on 2 problems, which the second one is considerably more challenging than the first. But I want you to work in groups, work with partners, try to get through both examples. And if you need a little bit of help or you need some hints, then just raise your hand and I'll come around, or Jacob will come around and we'll help you out. Okay? Okay, please take a couple seconds to write down both of the problems because I forgot my laptop charger today. So I'm going to have to turn the screen off in a second. But that just means I'm going to have to stop the recording. I can still just plug the iPad in. So let's just write them down so that I can momentarily switch the screen. All right, we all got them written down? Someone say no? All good now? Okay.